Hey, thanks very much for the um, invitation and introduction to to participate in this workshop. I'm sorry for the voice. I have a terrible cold, so I will try my best. Today I have actually three talks, so if you want to follow me today, it will be quite intense from hybrid modeling to causality and back. But in any case, I mean, these talks are happening actually in different places. So I don't know, maybe you want to take the tram and the metro with me. So today I wanted to talk about these two fields that I'm really excited about, which are hybrid modeling and causal machine learning, and how can we do our best in trying to you know to extract as much information and knowledge or understanding as possible from data, in particular system. This is not going well. Okay, it is. So I think it goes without saying that now we are kind of in this AI revolution, not only weather forecasting, but in many other disciplines. And we are seeing, ENSO forecasts that are more accurate or precipitation forecasting with deep learning algorithms. And of course, this weather revolution as AI for weather revolution is actually happening. You just blink and there is another model out there that promises or outperforms the previous ones. Um, but in this presentation and this work that we are trying to conduct in my lab, we are not that much interested in the what question. I mean, predicting things or accurately predicting things, but more than understanding processes through data analysis, right? So this is just what I consider like the roadmap of sciences in when it comes to machine learning. And as I said, we are not really or not much interested in beating the number, but more on answering questions about the why and the how. I will try to cover these things. Part one, more dedicated to encode knowledge in machine learning. Part two, more extracting knowledge from machine learning, right? Or from data, right? So yeah, there's like a long list of things, but you would immediately see what I'm talking about, right? So let's go to part one. Um, in part one and two, actually, they are kind of an intersection, right? There is an interplay, right? So, when you want to apply AI in the earth sciences, you are basically always or almost always asking questions about, oh, can I improve the algorithm? Can I make it faster? Can I make it better? Can I emulate some parts that are uncertain? Can I parameterize better the models that we are kind of trusting? Can I learn algorithms that can be, well calibrated, that can provide uncertainties? We are always asking questions about how the model is performing and what can we learn by doing this data analysis process, right? So I highlighted this kind of four different fields of discovering either laws or equations, learn to calibrate or parameterize models, emulate models. That's also a very active field, and of course encode knowledge. No, I will only treat two of them, the encoding and decoding parts, through hybrid modeling and causality. So let's go for part one. Probably, I mean, I call it here hybrid machine learning, but you will probably see this in different flavors. Physics aware, physics informed, knowledge guided, domain science guided, whatever, right? So in reality, it's just encoding knowledge in whatever funky deep learning architecture, or not necessarily deep learning architecture, right? Um, so everything actually started, at least for me, um, well, attending AGU some years ago. That was the first slide I saw, right? I enter a room and I said, oh, that looks pretty interesting. No, this is an old quote, models without data, fantasy, data without models are chaos, or kind of chaos. So from there, we started thinking about how to combine data, models, prior knowledge, and how could these things could be, how how one could live in this interplay, right, between physics and machine learning. So from there, some colleagues we started thinking and defined kind of a roadmap of this intersection between deep learning and process understanding for data-driven or system science. You can find like a very, in my opinion, very nice paper, no equations at all, very simple to digest and to follow, and some ideas for the future. And since then, I think that we have seen like quite successful stories of hybrid models out there, not only for weather forecasting and climate, but in many other fields, not only in earth science. Let me just take a look at several flavors on which one can actually incorporate knowledge into in machine learning. So the first one is about playing with the laws. You can play with the laws, you can play with the architecture, you can play with both things at the same time. This is just an example of how to incorporate knowledge in the cost function. And this is a kind of an old paper, but very interesting, right? Here, the authors were interested in predicting temperature, different depths in lakes across the US, and they managed to incorporate this extra regularizer, omega, there, that basically tries to penalize all the sum of all the violations. The goal is predicting temperature, but there is a clear and a very well-known relationship between temperature and density, right? So you can incorporate this in the function on the regularizer that actually forces smooth transitions across the different layers, right? So what the authors observed is that the accuracy was not really improved that much, but they really observed kind of a better extrapolation capabilities. In principle, one expects that let's say that physics is invariant. So it should work in one lake or another, right? So this is like the general aim, and this is what you actually attain, not very much of accuracy or of gain in accuracy, but more of kind of a gain in extrapolation. And this is a very cool thing to have, right? We observed this omega and said, oh yeah, but this omega is nice, but it only considers one-to-one, right? So it's a univariate. So you are only comparing temperature predictions with the density associated with that, right? And we came up with an extension of this, not with deep learning architectures, but with kernel methods and Gaussian processes. And it's very nice because in this setup, when you define this omega, well, we call it I because it's a kind of an independence criterion. You can force dependence or independence to whatever variable or ancillary variable. Everything comes in closed form, which is very cool because you only have to invert the matrix. That's very nice, right? And moreover, we find out like a very, very nice relationship or interpretation in terms of Gaussian processes, so you can actually see what you're actually doing, right? So there is an interpretation for the parameters, and then you can start designing proper priors as well from there, right? Just a little example here. Here, this is just another example. So we wanted to predict temperature anomalies in the last century, and you can be dependent or independent to natural or anthropogenic forcing. In this case, you can get better predictions or worse predictions, right? And then you end up with this kind of Pareto front. I actually urge you to play with Pareto fronts, not just beat the number or accuracy numbers, but try to plot always like, I don't know, consistency or computational cost or things like that, because that will tell you the real truth. If your model is better or worse, right? You have to consider multi-criteria. In this case, you have in the x-axis the RMSE, and then in the y-axis you have H6, which is the independence criteria that we are using. We were trying to fit a Gaussian process that it should be kind of dependent or independent to aerosols emissions, to greenhouse gas emissions, to land use change, all these things, right? So you have different Pareto fronts, and then from there you can actually summarize this in just basically the sum the area under these curves, and then you end up with kind of a ranking of consistency, accuracy altogether, right? That tells you like the obvious story that we all know, that aerosols and greenhouse gases are actually not only necessary to predict well, but also they need to be there to be consistent with the physics, right? So this is like one of the methods, right? So you can play with the laws, but people have been playing with the architecture as well, right? Because most of the knowledge, and very often it comes in the form of ODEs or PDEs, right? So what you can do there is to design an architecture that considers these peculiarities of the ODEs, and then just fit in a kind of a layer there, and then you learn end to end all not only the parameters of the neural network, but also the parameters of the ODE. This is one of the first examples, the PINs, physics-informed neural networks. Since then, there have been like many different algorithms to go not only with ODEs, but PDEs, stochastic PDEs, etc. This is just the last picture here. It just shows you an example. which is the neural GCM algorithm from Google DeepMind. It was presented last year, and it has like a double branch here in the middle in the encoder part, where you have a dynamic core and learn, let's say, physics representation module, and then you learn everything end to end. And it adds not only a bit of accuracy and extrapolation, but also consistency, right, with the physics processes that you already know. So you can play with those as well. And here's an example, let's say, not on weather, but more in the hydrological cycle. This was, let's say, the first global hydrological model, hybrid model that some colleagues in Jena, they presented some years ago. Basically, don't feel too much overwhelmed by this figure on the left, right? So there are like only 3 blocks, A, B, C. So basically, you start from some input meteorological forcings, like precipitation, temperature, radiation, right? So this time series there on the left. Then you create an embedding, then you feed a neural network on the B part. And this neural network, instead of predicting directly the, let's say, runoff or evapotranspiration, it just spit out these red parameters there in the middle, right? These alpha parameters. These alpha parameters are then entering into balance equations or bucket model, as they call it in hydrology. And this is the let's say the C part, the hydrological model. It's a very simple model. It's just basically balancing things out, and then it provides you the final predictions, right? In this case, 2 predictions of total runoff and evapotranspiration. The cool thing is that, well, you are kind of forcing first the model to behave as it should be. So considering these balance equations, respecting those, that they should be there. In the process, you learn things. You learn these alphas that you couldn't have learned otherwise, right? Because if you just take a big neural network, then alphas are unknown and you don't really know what is going on inside, right? So then you can actually see how these alphas react and how they behave in front of, let's say, extreme events, for example, right? And then you have like a better parameterization of the system, right? So these are cool things that you can get in the past when doing these hybrid model exercises. In our lab, we have done this for other settings. In this particular case, we were interested in drought monitoring, in drought detection. Again, don't feel too overwhelmed by this funky figure. Basically, 2 branches, up, down. So the first branch is basically ingesting all kind of essential climate variable, the spatial temporal data cubes, like from GPP, NDVI, salt moisture, all different variables. The bottom one is basically ingesting indices, all kind of indices, drought indices that are basically computed accounting for the last, let's say, 10 years or 20 years or something like that. So they are very fine-tuned. They are like, concrete parameterizations that are quite robust in general, not super accurate, but very, very robust, right? So we wanted to combine those pieces of information. Of course, you could just put together everything and then fit it on our network, but we wanted to learn something out of this. So basically, we learn autoencoders, we learn latent representations, and play again as well with the loss. So the loss here has 3 terms. The first term is just obviously the reconstruction of both pieces of information. And the second term is just a contrastive loss function. And the third term, which is what does kind of the magic, it tries to align the 2 latent representations, the one from the observational data and the one from models, right? So it's just basically a co-outline divergence, right? So we observed something similar to the case that I showed you before on the lakes. Here, we try to analyze different droughts in different places in Europe. And we observed like a little bit of gain in accuracy, but what it was more surprising, it was like that the model could extrapolate in space and in time, capturing different droughts and different events quite nicely. Just give me a sec. Good. So this is just one form of interaction, right, between machine learning and domain knowledge. There is another one that has been typically done for decades already, which is simulation, right? So you want to replace some very costly parts of a model or maybe subcomponents of a model, and then you want to replace it with machine learning because of obvious reasons. The most arguable reason is computational accuracy, efficiency, right? So you want things to go faster, right? So this is actually the setup, right? So you have some parameters or some variables, and they go through a radiative transfer model in remote sensing or whatever physical model. This is the forward pass. It will give you some observations, X. And then here you have like two different problems, right? You want to emulate this costly model RTM, or you may want to retrieve, you want to compute the inverse of that G function, and that's called retrieval, right? So you want to retrieve some parameters from some observation. I'm gonna focus only on the first pass, on the forward pass. And in this field, at least in RTMs and at least in remote sensing, we have been comparing a lot of methods, a lot of standard machine learning models, right? Remember that this is typically IID data because they come from simulations without any spatial structure in principle, even though that there are RTMs that they consider so. In this case, typically Gaussian processes are performing very well. Remember, we are not able to simulate tons and tons of data, so it's moderate sizes lookup tables that you have to invert or model. So in this case, in this scenario, GPs are performing very well. When you run a sensitivity analysis here in the middle, it is really hard to say that, I mean, which one, or you cannot really tell which one is the true one and which one is a machine learning emulator, right? So that's very cool, no? Because it tells you that these machine learning models have captured some sense of physics, right? Encoded in the RTMs, right? And of course you gain something, right? You gain speed up, right? So simulating pixels in this case, in these RTMs, you pass from seconds to milliseconds, right? So this is very nice because you can simulate much better, right? You have this sensitivity analysis that tells you, you gain some trust, right? You have some trust in the model. But there is an extra thing that people is not really exploiting too much with the simulation, that it is that in principle, and at least when using Gaussian processes, you can have like a full treatment of uncertainty, not only quantification, but also propagation of uncertainty through the Gaussian process. There are like closed form solutions for doing that, right? And this is very, very convenient. But still, in this realm of emulation with Gaussian processes, for example, you are confronted with the biggest bottleneck, right? Which is I still need to run my RTM and generate data, right? And this can be very costly, especially for some RTMs, you can spend months just simulating data, then your machine learning exercise is like very fast, right? So we came up with a greedy algorithm. We call it a GAPI. And it is quite efficient, actually, because you start from very few simulated data, and then you construct an acquisition function from the very same Gaussian process that will tell you where to sample. In the first step, basically, the Gaussian process is used as an interpolator with as few examples that you have, just overfits the data, right? And then from the equation that you have in GPs, you can compute two terms. In these two terms that we are computing, one is the diversity term, and the other one is the geometry term. The diversity term is basically the predictive uncertainty of Gaussian processes. That's very, very convenient. So since you don't have too much data at the very beginning, the uncertainty bars will be quite big in certain regions of the space. The geometry term, you can also compute it in closed form solution, and it is basically has to do with the weirdness of the function that you're learning, right? So we, intuitively try to enforce or try to sample more in very uncertain regions, but also in where the function is actually behaving erratically, right? So you construct the acquisition function. This is very fast because everything comes in closed form. And then you just sample more there, right? Then you collect some more data, and then iteratively you improve the results. You gain two things. You gain an optimal lookup table, right? Like quite compact, the optimal sample points that will conform your database, and then you end up with the optimal emulator in the end, right? Okay, so far so good. So we have seen like two ways of interacting, right? You can play with the laws, with architecture, or you can just intrinsically work together with the data generating process and the inversion and the forward passes, right? But this is not really understanding anything, right? Or maybe very little, right? You learn some parameterizations, you learn some parameters here and there, right? Let's go for I think that the most fundamental part, which is about how do we answer, rather, the why questions, right? And it has to do with causality. Yes, there's a lot of interest these days in causality in general, but also I think in the neurosciences in particular. There are if you want to start in this field, I would strongly recommend you these papers. I mean, it's not because I'm an author here, but they are very very easy to digest. Review papers, perspective papers that tells you more or less. We try to organize more or less the field, which are the tools. There are even associated benchmarks and everything like that, right? So I would strongly recommend those. Let me just start with a standard causal discovery. Very often we want to discover things. We want to uncover relationships between data, between variables, and yeah, we want to do it like in as agnostic as possible, right? So this is causal discovery. There are a lot of methods for doing this. The most traditional one, the most standard one, it is the Granger causality. Basically, in Granger causality, you only have to run 2 autoregressive models. We are here working with time series, so you try to create a model for predicting the future of Y from the past of Y, and another one predicting the future of Y from the past of Y, and the past of X, right? And if this later model is better, then you decide that this is the right direction, or the causal direction, because it is actually helping, right? But in Granger causalities, you may imagine these are autoregressive models. So you're assuming stationarity, you're assuming linearity. So these are 2 very important problems, right? That we're facing when we are analyzing our system data, right? So typically processes are nonlinear, and they are non-stationary, right? So we extended this Granger causality with kernels. So we have nonlinearity because of the kernel trick. And also, we design a kernel that actually can be adapted online. So you learn these non-stationarities as well. And here I'm showing you just a very simple example. On the left, you have the lag autocorrelation, the maximum lag autocorrelation, correlation between El Nino time series and Sol motion. So for Sol motion, in every grid cell, you have a time series, right, for the last decade. And then you just find which is the maximum lag correlation, right? And you see a lot of patterns, a lot of regions in the world are actually popping up, right, on the left. The thing is that when you apply Granger causality, or in particular this nonlinear Granger causality, most of them, the ones circled in red, they're basically spurious correlations. They are not identified as causal or Granger causal here. Only the very, the ones highlighted in green, they have to do with very dry or very wet regions actually in the plant. So this is something very important to do. Disregard spurious correlations and identify the real causes or the Granger causes here. There are many other methods. I mean, this is just one example. And I didn't want to cover all the methods. There are so many, right? I think that this is quite practical as well, and very well regarded in the community. It has to do with, it is called PCMCI. The PC algorithm is an optimal way to exploit all or to estimate efficiently all the conditional independence tests between all the variables involved. And people have been using it for many things, right? For causal discovery. And in this case, I wanted to show you an example where you can use causality to intercompare data and models, right? Instead of imagine that you depart from the very top, you have observational data that evolve in space and time, right? And then you have many different flavors of different models telling you different realities, right? And then you want to, let's say, quantify which of these model simulations reflect better the causal structure in the what generated that generated the observations, right? So the first step is basically applying PCA there, or PCA Varimax. People is using this. So you get some modes of variability in space, in time, and then every node of the causal graph, you learn a causal graph for both observational data and the model simulation. So you have many different graphs, right? Look, these graphs are, of course, directed as cyclic graphs. So you don't have cycles and you have edges, right? So you have arrows there, no? So how to compare all these causal graphs is really, a whole thing in itself. And one possible metric is just the F1 squared. So how many edges are in common, how many identifications have your model, etc., right? The authors came out with this tune F1 score, and that they can evaluate, let's say, the realistic behavior of different models compared to observational. I think that observations here are basically area 5 data, right? So let's assume that these are observations, right? So you can come up with metrics, with causal metrics, right? So you can identify which of the models is actually incorporating more causal structure compared to the observations, right? Let's assume that we observe nature and nature is the truth and it's not misleading us, right? So let's assume this. But as you may imagine here, there is like a long bottleneck and with many potential flaws. You have to select how many components of this array. You have to select how many basically nodes availability, how many, or how do you tune the PCMCI? There are many different type of parameters to tune, and then you have to select the metric. So, wow, I think that it's gonna be relatively easy. You will be, misled or things can go very, very wrong with so many of our parameters, no? Another way is to treat the data as it is, right? So spatial and temporal evolving, right? So this is the actual very recent field that people is quite excited about, which is learning causal representations of the data. I'm going to show you a very simple example, a method that we generated some years ago that tries to exploit the spatial and temporal redundancies all at once. So you don't have to do PCA, assume linearity, and then extra components and blah, blah, blah. Here, basically, we wanted to answer the question, a very similar question to the previous one, in which is NDVI affecting, or how NDVI is actually affecting different regions in the planet, saying how it's affecting vegetation in our case. So we construct an autoencoder trying to reconstruct the spatial temporal cubes of NDVI. And on top of that, we force the latent representation to be Granger causal with ENSO, with El Nino. Okay? You can create this loss term here. Remember the Granger causal, the Granger causal term, it has to have two things, right? Two regressions, one with and without ENSO, right? Or the past of ENSO, no? So you can create this thing. Of course, it is no closed form anymore because the funky architecture of autoencoders. But then you have introduced this beta parameter that basically tells you or tries to trade off between reconstruction of vegetation and Granger causal relationships with ENSO. No? So you can get some latent functions there in the representation of the autoencoder. Without any Granger penalization, you get these things, and it is really hard to believe that the most correlated function with ENSO is this one highlighted in red. Remember, we are talking about lag correlation, so more or less you can think that if you displace this red curve towards the past, maybe you find this correlation, right? When you introduce just a little bit of Granger penalization, then you end up with this one, right? It is not that you are super interested in optimizing or maximizing the correlation. What you are really interested in is in retrieving the most Granger causal relation as possible. And by construction, this method will return the most Granger causal latent function as the top one, right? And the second one, and the third, etc. Right? So the first one is actually that one. And then you want to analyze in space and in time what is actually driving vegetation impacts, right? So for that, well, you have to analyze the encoder. And we basically applied a particular technique of explainable AI technique called integrated gradients, where you can analyze the encoder, right? With a little bit of Granger penalization on the top row, you see that there is the impacts on vegetation in Africa in particular they're like capture much better and faster, let's say. The impacts, and most of the impacts reported in the African continent and in that period were actually reported at the very beginning of the 2016. And you can actually identify those or the potential, you can anticipate the potential impact of ENSO on vegetation like some months before, right? This is aggregated over the year, right? Okay, so I think that, of course, the immediate question is, oh, yeah, but now we are in the quest for these new oracles of foundation models, right? So we want this magic box that will solve all our problems, but maybe these boxes are not really causal. They don't know anything causal inside, right? So maybe we could do something with them to make them causal, or at least analyze them in causal terms. That could be interesting things and ways to go, right? And if you look at the literature for foundational models, you see that there are of many flavors, right? So you have geospatial, meteorological foundational models, and you have also impact foundational models. Not many, but I think this is a possible and a very useful way to go. Instead of predicting the variable itself, maybe at least in particular, for this field of early warning systems and evaluation of the risk and impact assessment, I think it is good to go directly to the impacts, right? Instead of predicting temperatures or anomalies of vegetation variations, etc., you go directly to the question, right? To food insecurity, to migrations, to vegetation stress, or things like that, right? But the promise is to use everything that you have at hand, right? So methodological simulations, then you want to include remote sensing, etc., right? In this paper, it was more focusing on early warning of complex climate risks. So we hypothesize this is just a perspective. There's nothing actually implemented, but this is the idea. The idea is to, of course, harvest as much information as possible, not only meteorological, but remote sensing, time series, text, audio, whatever. Then you learn your magic latent representation. Go directly to what it really matters in our field of early warning systems. So risk mapping, impact assessment, and of course the communication of risk, which is the last mile in this chain, right? Our, let's say, proposal here is to create modules that interact with this latent representation, similar or in the same fashion that I just presented with the Granger autoencoder, right? So you cannot expect that this data representation will be causal, but maybe in the training you can actually force some causality inside, right? So this causal inference term should be connected with the data representation, but also of course with the data itself. And this is just a proposal, and there are some examples out there already that have adopted similar strategies. But yeah, for the sake of time, I'll kind of skip it. So basically, I will come to the conclusions of the presentation. We can interact, domain scientists, functional scientists in many different ways, and we should actually, in many different problems in the Earth system side, right? So not only emulation, but prediction, consistency, and of course, trying to understand processes through the data analysis pipelines, no? Not just be fine with a little bit of improvement in accuracy, but try to understand what is going on, right? So my first take is to understand processes can be done more efficiently and I think much better by integrating this agnostic point of view of data processing with domain knowledge, and then the take two is understanding complex systems means answering causal queries. Now, most of us, we are not really answering or asking causal questions, right? Most of the time, just give me the data, I will smash the data, and I will give you a model that fits it, right? But maybe this is not the interesting thing. We want to understand causal relationships and questions, right? Okay, that was it. Thank you very much.